All right. Hi, everybody. So today I'll be talking about LLRBs, also known as left-leaning red flag trees. Okay, so what are LLRBs? Well, LLRBs are trees that ensure that we maintain a balanced structure. Now recall from last week that we already discussed about a tree that maintains a balanced structure, the 2-3 tree. So why would we ever need an LLRB over a 2-3 tree? Well, the answer to that is that it's actually easier to implement an LLRB than it is to implement a 2-3 tree. So before I get into the LLRB, I do want to talk about a couple of operations. The first operation I want to talk about is the rotate left operation. So suppose we have a node n and we call rotate left on n. What that's going to do is it's going to take the right child of n, let's call this right child x, and it's going to make n the new left child of x. So let's look at this pictorially. Suppose I have this tree and I call rotate left on f. What it's going to do is we're going to get the right child of f, which is h, and we're going to make f the left child of h. But notice here that g is currently the left child of h. What's going to happen to g? Do we just throw it away? Well, notice that g is in this right subtree of f, and when we rotate f to the left, f is not going to have a right child, and we can just stick g as f's right child. And because, like I said before, g is already in the subtree, in the right subtree of f, we know that g is going to be greater than f, so this is a safe operation. Okay, so this is what the tree looks like when we rotate left on f. The next operation I want to talk about is the rotate right operation. So again, suppose we have a node n and we call rotate right on n. What that's going to do is it's going to take the left child of n, and let's call this left child x, and we're going to make n be the new right child of x. So again, let's go back to this tree. Let's say I call rotate right on f. What it's going to do is we're going to get f's left child, which is b, and we're going to make f be the new right child of b. And again, b's current right child, which contains a subtree of d, c, and e, can now be the new left child of f. And that's, again, a safe operation because DC, the nodes D, C, and E, this subtree here, is already to the left of f. Okay, so this is what it looks like when we call rotate right on f. And the final operation I want to talk about is the color flip operation. So again, suppose we have a node n. What the color flip operation does, it's going to take all the links that are connected to n, and it's going to flip the color of the links. So any black link that is attached to node n is now going to be a red link. Any red link that's attached to n is now a black link. And again, going back to this tree, suppose I call color flip on b. Well, the links that connect A and B and D and D are both red, so they're now going to be black. And the link that connects B and F is black, and we're going to turn it into a red link now. Okay, so that's what we do. And now I want to move on and talk about LLRB insertions. So when you insert to an LLRB, you first insert just like you would for a BSD. So if an element is less than the root, we move and look in the left subtree. If an element is greater than the root, we'll go to the right subtree and search there. However, when you insert a node, we insert a node with a red link. And this insertion could either violate an LLRB property, or it can be completely fine. If there is a violation, however, we do need to fix it with one of the operations that I mentioned earlier. So what are the 3 LLRB violations? Well, the first violation is if we have a red leading link. Because this is called a left-leaning red flag tree, we want all our red links to be leaning to the left. So consider we have a node n, and the edge to the right child of n is red, and the edge to the left child is black. Well, this is considered a red-leaning link, and that's our first violation. The second violation is if we have two consecutive red links. So consider we have a node n, the edge to the left child of n, and the edge connecting n's left child to its left child are both red. In that case, we have two consecutive red links, and that is also a violation. Violation number 3 happens when both children are red. So consider we have a node n, and the children of the node are both connected to the node with a red edge. Okay, so those are 3 violations of an LLRB. How do we fix them? Well, for the first violation, our fix is going to be to rotate left on n. For the second violation, when we have 2 consecutive red links, our fix is to rotate right on n. And the third violation, when we have both children are red, is to color flip on n. And an important note is that it is possible that a rotation or a flip operation will cause an additional violation that needs fixing. So just because I do a rotate right, a rotate left, or a color flip doesn't mean that the resulting tree is completely fine. After doing those operations, that could cause an additional violation. So be careful with that.